Now, okay, so we're continuing on inverse functions. So we're asked to find the inverse functions for the following. F of x equals x squared minus 2. So I don't know how you have been taught to set it up, but I always first of all rewrite the function. Y equals. That's my first favourite little step to do. And then after that, I'm going to swap it over. That's my favourite way. X equals y squared minus 2. Then you rearrange to make y the subject in whatever way you do. What? Do you want to try? Oh, yeah, Krista?
You want to add 2 to the other side?
Yeah, good. Add 2 to both sides and then finish the little thing off.
Then you want to square root of to get rid of the square.
Yep. And this is all lovely, but they can be a bit fussy. They love you to write your final answer
As
F
negative 1.
Exactly, yeah. F negative 1x equals plus 2. Ooh, what went a bit funny there. So sometimes you might see a plus or minus written out the front as well, just in case you ever see that in the answers, because even roots have positive and negative answers, so sometimes they might have put a plus and minus out the front in the textbook. Yeah, so it's nice. It's just practicing transposition, really, isn't it? So that's what we're doing, practicing the algebra stuff. Same thing, I like to just rewrite the function, y equals, and then go into swapping things over. Swapping your x and your y. And then you rearrange. So how do you deal with, what's the opposite of square rooting?
Square.
Yeah, good. Nice one. And then would you deal with the 4 or the 3?
Subtract 4, or you can do
Yeah.
5, 3, 1.
Actually, good point. Subtract 4 first.
Yeah,
Yeah, you're right, yeah. So x squared subtract 4 equals 3y. And then, like Krista said, divide by 3. And just be aware, if it was g of x, you would have to use g minus 1x in your final answer.
Take paper.
I need the...
No, you
No?
took mine.
Let's see. There you go, take... Oh, you need I think this must be
I
mine.
had it. You just took the one that I was working on.
You mean this?
Yeah, I started this page and then I started stapling and then you took it.
Where am I then? Probably sitting around somewhere. I don't even need one. I probably stuck it back in there. Yeah. Okay, good. Okay. So equals that one, x squared minus 4 over 3. And we continue on. Feel free to just run through the page. I've given you a clue for this one. We might need to use logs once we start to rearrange. So we've got to first of all go through everything. As before, rewrite the function. Swap it over. And because we need to make y the subject, when we've got an unknown exponent, what we tend to do is we log both sides. Or you could go straight to just rewriting into log form. So you could either log both sides and then put y at the front and that kind of thing and divide off log 2. Or you could go straight to putting it into log form. What do I mean by that? So
Log x equals log 2 to the power 1.
yeah, something like that. So in which case, in this one, which one is the base?
2.
2, yeah, the base is 2. So down here we put log 2, because the base is 2. And what goes here? And then what goes here?
Log 2.
Yeah, that's right. Because if you rewrote this into exponential form, remember the base to the power of the exponent equals x, which is base to the power of the...
Wait, so you can't log both sides? That's what I did.
You could, and you'll get an equivalent answer. In fact, let's do both. I'll do both. Yeah.
I just erased it.
You can unerase it. So this one, if you do this version, you're done already. And it is f minus 1 x we'll try both versions, one where we log both sides instead. And it's an equivalent answer, so we would go x equals 2 to the y. So then we could log both sides. I'll put the log in red to show that we've logged it. Log x equals log 2 to the y. So just log both sides. So then we get log x equals y log 2. And then we just divide off log 2 on both sides. So weirdly enough, this green one here is the same as that green one there. Oh. Yeah, but they mean the same thing. If you use, remember when we did logs, there's a thing called the change of base rule. If you use the change of base rule, that bit turns into that. Because that, what we'll have done is we'll have changed the base to base 10. Change them both to base 10, and then that thing pops there and that thing pops there according to the change of base rule. So using the change of base rule on this makes that become that. So f minus 1x equals log x. It's not like one version is better than the other at all. Like it's not like, you know, how sometimes there's one version that's considered more simplified. That's not the case. They're both considered equally as good. That one's just easier, but less work. But still, it's good to practice that method, because then in this one you're practicing using the log laws more, so it might help you to remember them more. So both are great. Any questions about that one? What kind of function was the original function, by the way? Exponential, yeah. Keep trying to go back to that. And the top one, what kind of function is the original?
Quadratic.
Yeah, quadratic. This one doesn't have any special name. It's a square root function, I guess we could call it that. What kind of function is this one? Linear. Good. What's its y-intercept?
1.
And does it have a positive or a negative gradient?
Negative.
Good. Y equals negative 4x plus 1. Yeah. Are you feeling challenged? And then this is an easy one. So, do you deal with the negative 4 first or the 1?
The 1.
The 1, yeah. It's like the furthest away from the y. Yeah. And then, do that, negative 4. Yeah, you can sort of change that a bit. Yeah, good. So, Lauren just picked out, you might find in textbooks and in answer schemes, they're not so keen on the negative on the bottom, but not, to be honest, it's not a big deal. Yeah. If you change it to positive 4, what would that make the numerator now, Lauren?
Negative x plus 1.
Yeah, negative x plus 1.
You just literally change all the signs?
Yeah, or 1 minus x as well. Quite often, textbooks, they love to put the positive at the front. Negative x plus 1 is not wrong at all. Just showing you that the textbooks could do that. So this first one is actually not wrong, but the second one is the way the textbooks like it. Some mathematicians just think that looks prettier than that. So again, it's not saying that that's a superior answer necessarily, it's just the mathematicians like to present it that way. They find the negatives here and negatives there all good. This one gives them a dopamine rush and that one doesn't.
A dopamine rush?
Remember, like the thing where mathematicians were getting their brains scanned and looking at beautiful equations?
And then when they saw beautiful equations, that's a brain.
Yeah, so if they're being brain scanned, this one would get the happy brain, part of their brain going, and this one wouldn't as much. Oh yeah, and be aware, these were all f of x. I should have mixed it up and put some g of x's in there. If it was g of x, we'd have to make it g negative 1x, of course. Oh yeah, so notice I was kind of boring. I made them all f of x. F of x, but if they had a different letter, like g of x, then you just have g minus 1x. Or h of x, yeah.
Okay.
That's all it was, yeah. But
I'm confused because then you said we didn't need the negative.
I was mumbling. It was probably because when I was just saying negative 1x, that's that kind of thing, yep. So yeah, that was just back to the function notation, just use the notation they've got. And we still have a few more. Let's roll through these. One third x minus 7. Do we deal with the 1, the 3, or the 7 first? 7, yeah. Oh, hang on, I haven't swapped them over. Sometimes these kind of ones confuse people, like if you've got a third at the front. Does anyone have any suggestions for what we might do? But, yeah, so therefore will the left hand side become 3x plus 7? Oh, what will it be instead?
3x plus 21.
Yeah, 3x plus 21, yeah. So dividing by a third, the opposite is to multiply by 3. You could think of it as timesing by 3, dividing by 1, which overall is like timesing by 3. And you can go straight to the expanded version if you prefer. Equals y. And then with f of x again, so go f minus 1x. So Sarah, you'll just catch up on this later, will you? Yeah, because you're just missing the earlier stuff, yeah. So you're just catching up on the earlier videos. Yeah, question?
So if you multiply, I'm confused because 1 divided by 1/3 divided by a third is the same thing as that just gives you 3 over 1. So how come it's not 3y?
Which bit? From here?
Yeah.
Going to there?
I don't understand that.
Oh, right. So in a way you can think of that. That's like 1y divided by 3. So you could almost think of that as being the same as y over 3. If you agree? Like 1/3 y is like saying 1y over 3. So if that helps, y over 3, and then all you would have to do is times the 3. Times by 3 over here. So 1/3 y is the same thing as y over 3, like 1y over 3. Which might help you make it a bit easier to see.
Yeah, it makes it
where you're timesing by 3, just timesing by 3 over there. I need to swap over this one. So x equals 1 minus 3x over 2. Do we deal with the 1, the 3, or the 2 first? The 2. What mistake did I make in my second line there? I did. Yeah, I did x twice. I'm looking at it going, what?
I don't know. Yeah.
Yeah, exactly. Yeah, I read it.
Yeah, I navigate over
That's a bit better. So now do we deal with the 1 or the 3?
The 1.
Negative 3y, yeah. And now what do I do? Do I add 3?
divide by negative 3.
Do you change it? Like, would it be negative
Maybe we'll do that. So at the moment the mathematicians, if their brains were getting scanned, they wouldn't be getting a dopamine rush. So,
Oh my god.
so how could we, like we did with the other one?
You multiply by negative 1 over 1.
Yeah, that's a good idea. Thinking of it as negative 1 over negative 1. Yeah. Yeah. Because it would be like minus 2x plus 1. But the mathematicians like to do that. Over 3. Yeah. Minus 2x plus 1. These are just the way the textbook or the mark scheme might display their answers. This is not wrong. So this is technically right. That's the way they might display the answers on the textbook. So it's good to be aware of that so you don't kind of get confused and think you're saying wrong.
Oh my god.
Anyone have questions about that stuff?
I learned it's R, you said all of that.
Next one. Graphs of inverse functions. Did you guys do graphs of inverse functions at all last year?
No, I don't think so.
Yeah, because it's not really officially in your syllabus, but it might have been brushed over.
No.
We did the inverse of y equals x.
Yes,
It's to do with the line y equals x, yeah. So graphs of inverse functions, we'll just do it as if you haven't learned it before, that's fine. Inverse functions.
Why is there like a little O?
Where?
No, like the first page with the assignment.
it just means like after
Where?
G.
Oh yeah, okay, that's for the funny terminology, good. Yeah, Lauren asked a good question about the topic assignment. See, like on the front page of the topic assignment, 1B, it's got the new funny terminology. Like remember in the past we used F for composite functions, we used F brackets F of X.
Oh yeah.
But in SL, they can use the old version and they can use this new funky version. F of G. See how the O is kind of like this funny little, it's kind of like an of. Like that there. Yeah. That means a composite function. Yes, and you'll see that pop up. Both versions can pop up in SL.
Like F bracket G X bracket.
Yeah.
Yeah.
Okay.
Yeah, that's what it means.
No.
Not equal 7, it means
Oh.
F that G X 7.
So the X is 7.
Yeah.
Yeah, but the X is F
Bracket G bracket
7 bracket bracket bracket.
Bracket, what?
Yeah, it's kind of like that. You mean F of I just did it wrong. F of G of.
Yes, that's what it is.
Yeah, that's what it means. Yeah, you're right. F of G of 7 is what question 1B means. But the new funky terminology. Alright, inverse functions. So I missed the S on there. Inverse functions are a reflection across the line y equals. I just know because, and you don't have a background in this, so you weren't expected to know that.
We did do this.
You might have
I
done,
just didn't understand it.
yeah, it would have been just brushed over because it's not officially in the CIE course, the graphs of inverse functions. But-
Mr. Moore spent a lot of time on this
Yeah.
because I'm warning our
We definitely have
syllabus.
questions
And
on
make people
that.
But
understand.
it is one of those things where you just never know, like, you know, they might not state it explicitly on there, but then one year they might throw it on an exam.
It's just implied that
Yeah.
you should learn it.
Yeah, so it's one of the, yeah, and whereas we've never really seen it in the past in exams, but you never know what year they might throw it out there. So to avoid problems, they might teach it to you.
Log the ln y equals ln. Does that mean log ex?
Yeah.
Is that natural?
Yeah, log of v, yep, natural log. Correct. Okay, so inverse functions are a reflection across the line y equals x. Draw in and label this line of reflection, which is y equals x, on the graphs below. So we're going to do that with my nice line drawing tool. Let's make it nice and yellow. So the line y equals x would kind of, I'll do a vague here. Make it through there, and then I'll make it look a bit better. So what's important about the line y equals x is it's got to go through 0, 0. So it has to go through the coordinate 0, 0. Plus it also would have to go through 5 and 5. So does mine go through 5 and 5? Not really. Should be more in the middle.
That's correct.
And what, -5 and -5? Pretty alright, that's okay. So to point that out, I'll just draw these points. 5 and 5, -5 and -5. So see, I've just put in those 3 points, and they wanted to label it, so we'll label it y equals x. Does that make sense to these two graphs, y equals e to the x and y equals natural log x? Do they look like they're reflections across that line? Does that look like an axis of symmetry? Yeah. Yeah, it looks like a line of reflection, doesn't it? It's supposed to, but it's a bit stretched out on this board, so it looks a bit dodgy. Same thing here, they want us to draw it. A line. Let's do it again. Do it roughly. So it's got to match up with that, got to go through there. And kind of through there. Also, I can sort of see the way, like, see if I did it here, it's not quite a line of symmetry anymore. It's kind of got to go through.
What's going on there?
So see, there's a parabola here and a sideways parabola. It's got a, where they connect there, it's also, ooh, got a touch there. So visually I can sort of see it's not in the right spot. It should be kind of more there, shouldn't it? Just by the way it looks. But also -2, and -2, does it connect out? Yeah, it does. There's a point. Yeah. So, yeah, that's okay. That'll do. 0. See where they connect up? It should touch there as well. And 2 and 2, 4 and 4. Oh, I didn't do it very well. Okay, y equals x. So you should see, like, it's a bit stretched out. I should make that a little bit lower, maybe. Yeah, it's meant to be, see, it's meant to be kind of equal. That's bad, isn't it? It's hard to get it right in here. Okay, so see that it's kind of equal, it's meant to be sort of equal distance this way and that way, but the board, my board has stretched it out a bit. Hopefully on yours it looks okay. Okay, any questions about them? So you remember things like vertical line tests, one-to-one functions, many-to-one functions? If you forget it, it's okay. We're about to go through it again. So inverse functions apparently can only exist for special types of functions that are called one-to-one functions. So one-to-one. So a function is one-to-one if for each x in the domain there is exactly one y. So each x only matches up with one y.
Not following.
In the range, yeah. Exactly what does that mean? So if I just saw this, I wouldn't understand it either. So a function f is one-to-one if for each x there's only one y that it can connect to.
Oh, okay.
So let's we'll reiterate that, and I'll show you some examples through pictures as well on the next one.
Doesn't that go without saying this? Because every point has one x and one y.
I can put some little pictures here to demonstrate. So here's a classic example of a graph that's not one-to-one. What kind of graph is that?
A parabola.
Parabola, yeah. It's so see this x can connect up with that y.
Yeah.
But is there another x that can connect up with that y?
Oh.
Yeah. So this one is not one-to-one. An example of one that is one-to-one is linear functions. Linear functions. Are there any x's that connect up with the same y or vice versa? So this one is one-to-one. What's an example of another one that's not one-to-one? Maybe it's cubic. It's in this form. See a cubic. Trig graphs are examples of ones that aren't one-to-one as well. So this cubic is not one-to-one.
One-to-one.
Not one-to-one. Because this little x connects up to the same y as that little x would. They both connect up to the same y, so it's automatically not one-to-one. One-to-one just means each x has its own y value and vice versa.
So when it's like, it's more all linears are one-to-one.
Yeah, linears are pretty classic one-to-one functions. But you might find, as we'll sort of explain, if quite often they'll turn this into a one-to-one function, the parabola, but they'll restrict the domain. If they restrict the domain and say x is greater than 0, it means it's that graph, and suddenly it is one-to-one. So that's a thing that they can do. They can restrict the domain suddenly, and then it will become one-to-one. There's an example of that on the next page as well. This one like that. So that's a little overview of what we're just about to go on about on the next page. I thought I should also just remind you, a function is, this is not one-to-one. I'm trying to think what I was going on about. A function is not one-to-one if two different elements in the domain correspond to the same element in the range. So meaning like this little x here connects with that one, and this little x here also connects with the same y. Supposed to. So if two different x's correspond to the same y value, it's not one-to-one anymore. And if it was two y's connect to the same x, it's not even a function to begin with. That was the vertical line test, which I'll talk about on the next page. Recall, a vertical line test can be used to determine whether or not a something is also a function. What was the big umbrella term again? Relation, yes. A vertical line test can be used to determine whether or not a relation is also a function. A relation is anything kind of plotted on a coordinate plane, but a function is a specific type of relation. So this is just a recap of vertical line test. So the reason why I put these here was to decide are they functions or not. Is this cubic a function?
Yeah.
Yes.
Is a function, yeah? Because a vertical line could only ever cut it once. Yeah. That's what those are meant to be vertical lines anyway.
If it was the other way around, it would not be a function.
Yeah, exactly, yeah. If it was kind of going like that, a vertical line would cut it 2 or 3 times. So that was a cubic.
Horizontal line.
Like this.
So yeah, I was saying if it went like that instead, yeah. A vertical line would cut it more than once. What kind of function is this one?
Linear.
Linear, yeah. Just going back to recognizing what they are. What's its y-intercept vaguely?
One.
What's its gradient, roughly?
1/2.
A weird graph. How much has it gone? Yeah, it's gone across. Yeah, 1/2. And is it positive or negative?
Negative.
Yeah, negative because it's going down. Yeah, so down 1, across 2. What's that going? Oh yeah, is it a function? Yeah, it is a function. It is a function. This weird round circle? No. A function, yeah. Not a function. These are special equations, like, you know, that one would be, was it x squared plus y squared equals 9. That's what generates these circles. And then square root of 9 is 3. That's why it's got a radius of 3. Don't worry, you don't need to know those ones. So that one's not a function. That was just recap of earlier, like, you know, vertical line test stuff. So similarly, you can use a vertical line test to test whether or not it's a function to begin with. A quick way to determine whether or not it's a one-to-one function is also a horizontal line test. So, yeah, so that's a shortcut to decide whether or not it's a one-to-one function. Horizontal line tests can determine if it's one-to-one. Use a horizontal line test to determine if any of below are one-to-one functions. So they need to be a function to begin with, but I think I've picked ones that are all functions. Yeah, these ones are all functions. A vertical line test wouldn't cut any of those twice. So we can go straight into deciding, is it a one-to-one function or is it not one-to-one function? So it wants to know which one of these is one-to-one. So, yeah. What does that one tell us?
It's not.
Not, yeah. Put not down there. Minute.
Wait, but what about like
Wait, why'd you put 2?
In the middle? Oh, that's a good point.
Yeah, in the middle.
because that would
Yeah.
be 0? Does that count?
It's sort of meant to be like that. It's like a basic cubic. So it is just, it's very, very slowly hitting the origin. So technically it is.
Oh, so it doesn't.
Yeah, so it's a yes. Yeah, so it doesn't cut it to more than once. Yeah, it's just the way it looks. It looked like it was going along there, didn't it? But it was meant to be kind of more like a cubic. Kind of meant to be bit more like that.
So it is a.
It is a one-to-one. Yeah, because these horizontal lines are only cutting it once. It's just hard to see with the way it was drawn. It looked like that line that was kind of blinking along the line, but it was meant to be a bit more like that. Like it's meant to be a cubic function, where it's very gradually approaching the origin. And gradually moving it. What kind of graph does that one look like? What kind of function?
Logarithmic.
Yeah, good. That one looks like a logarithmic. These logarithmics, they kind of go up like that and then kind of level out a bit. And they have asymptotes. They have an asymptote, kind of vertical asymptote. Logarithmic function, vertical line test. Is it a one-to-one?
Yep.
It is, yeah. This is like a logistic function. You might learn about them a little bit later. Would you agree? It's a yes.
Yes.
It's a yeah. What kind of function is this one?
Exponential.
Yeah.
Good guess. Good guess.
Oh, we know what that is. It's a
Inverse. Reciprocal, sorry.
Reciprocal. Yeah.
Wait, what's the first one? Is actually, what's this one again?
The one up in the top corner.
Yeah.
That's a more like a logistic, which is not one that we learn about in this unit. But it's a logistic. Kind of makes these S kind of shapes. That appears to be a logistic. Reciprocal function. These have asymptotes. So reciprocal function, just reminding you, would have asymptote here and here. Same with the logarithmic. Would have had an asymptote. Going through there. What am I doing with that? Oh yeah, is this one 1-to-1?
No. Yeah.
Yes.
Yeah.
Oh, I'm on last one.
Yeah, so if you're not sure, cut once, cut
That
once.
one.
I was
Oh,
on
yeah.
I was on that too.
Oh, you're on it? Yeah. That one would be a yes. Yeah, it's this one.
Nah.
So it's a not. Not 1-to-1. So its inverse doesn't exist. Same with that one, its inverse doesn't exist. What kind of function is this, baby?
Maybe absolute.
Yeah.
I'm not absolutely sure.
That was a good one.
mean. Those are. I hate you. Pooping on my drink.
That's a good one. Okay, yep, so that one, as you said, is not. It's an absolute value function, it cuts twice. What kind of function do you think this one is?
Sign?
Yeah.
It looks like one. It's one that's appeared before as well. Just
Maybe it's a
different version.
sideways cubic, I don't know.
Yeah, no, you're right. It's a cubic. Yeah.
That is that one.
So cubics can look like these roller coaster types. Plus they could also be these kind of little slinky, what would you call that, a snake?
A slide.
A slide, yeah. Could be a slide.
Yeah.
Here, these ones have points of inflections, and these ones have kind of like maximums, minimums. So if it's more in its basic form, like just x cubed, or then it looks like that. But if it's kind of got like, you know, x cubed plus 5x squared plus 2x plus 1, they start to become big roller coaster types. Oh, by the way, is it 1-to-1?
No.
No, that's not. So its inverse doesn't exist. The only way we could make its inverse exist is if we restricted its domain to be like, you know, maybe something like from here up. So we've answered that one already. So as we said, they're all functions because the vertical line test would turn out that they're all functions. And then we just found out that the ones that are 1-to-1, this one, this one, this one, and this one, and that's good because we're meant to get 4 answers, so that's perfect. Sketch the graphs of the inverse of the 1-to-1 functions. That's going to be a bit hard to do because I've flooded it a bit.
You don't have to.
Let's do it vaguely here. So remember, you'd have your line y equals x, so just do it really roughly here. This one for the cubic, so for b, if you kind of reflected it across a line, y equals x, it would kind of like slink like that, wouldn't it? Do you think?
No, I don't know what you're saying.
Should we do it in yellow, just on the top?
Yeah.
Yeah, the line y equals x would cut through here,
Oh, yeah.
so it kind of be kind of going like that.
But that's one of the most popular inverse functions we had to draw.
It's a pretty dodgy one. Oh, well, yeah, you remember doing that? Yeah.
Yeah, that's like, we did it all the time.
And it probably would have been better if I had have, like, put in the line y equals x, but it takes me ages to do that on this board. So, y equals x would just kind of roughly go through there. So it kind of is like reflecting across there. The line y equals x, that one's a yes. So the line y equals x probably cuts through here.
Look, it's formed little website.
So its inverse is kind of going to go more like that. So see the inverse of a logarithmic is an exponential. Makes sense? An exponential and log are inverse functions of each other. Exponentials have asymptotes this way, logs have asymptotes in the vertical direction. So vaguely kind of like that. The logistic was a yes, so this one.
Why do you always?
So we just did a logistic one. Oh, and the other one was the reciprocal one. So in terms of drawing the reciprocal one, will it end up looking kind of pretty similar? Yeah, it'll look pretty similar in the end, so I'll just do it over here vaguely. The reciprocal one, when you reflect it across the line y equals x, will look pretty similar. So we're just doing it roughly. So in yellow. So in yellow is how we kind of sketch the inverse, or whatever else you did, colour you did, you write notes to yourself. Okay. Anyone have questions about that? Yep, a few people copying that down. So just let you do that. What are you singing?
Okay, I got so scared when I went to like that as a child. I would think swipe was my room, and I'd be like, swipe or no swiping. Yes. I love it. You know the conveyor belt at the store?
We're on to the next one.
The conveyor belt at the
Okay, let's get through the next 2 pages. Okay, so remember I was talking about like if the domain, thank you. Okay, so if the domain, a way we can make a function that's not one-to-one suddenly have an inverse that exists is we can restrict its domain. So if the domain of a function is restricted, like remember the parabola, if we kind of instead said, okay, a parabola but from this point onwards, then suddenly it might become one-to-one. So if the domain of a function is restricted, that might mean the function is now one-to-one, and that means its inverse function exists. That's the whole point of like, deciding are these functions one-to-one or not. It's deciding whether or not their inverse function actually exists or not. For example, the function y equals x minus 2 squared is what kind of function, by the way?
Quadratic.
Pretty obvious. Yep. Quadratic function which would normally not be one-to-one, but would be many to one. Yes, because meaning many in the domains, many x's could have the same y value. So many x's connect to the same y value. That's what a quadratic kind of looks like. Isn't it? Just reminding us. That kind of thing. However, if we restrict the domain to being x is greater than or equal to 2, because I should have just left that. See, the original x squared, an x squared function looks like that. Okay, so an original x squared looks like that, but according to transformations, x minus 2 squared, how does that transform this original graph?
Go to the right.
Yeah, to the right 2 units, yeah.
Wait, are we going to go over that?
Yeah, transformations is a thing as well. It's kind of embedded in here already, but we do it formally as well. Formula methodology. Yeah, transformations, this would be a horizontal transformation 2 units to the right. So instead of its vertex being at 0, 0, its vertex would be at 2, 0. So this one is x minus 2 squared. So to restrict its domain, one way we could restrict its domain is say that, okay, its domain is x is greater than or equal to 2. So meaning like from this part upwards only. So then the function is suddenly one-to-one. And its inverse function does exist. Another way they could restrict the domain, they could say x is less than 2. So it could just be that part instead. Yeah?
How are we going to get to that?
That's right. Horizontal transformations are always in the opposite direction to what they say. So if it was x plus 2, it would be 2 units less.
Way. Oh,
But
wow.
vertical transformations follow the pattern.
You can make a note about that.
Why don't they follow it?
Yeah, why don't they? Good point. Because if you plugged in x is 0 into there, you would get 0, 0 as your y. If you plugged in x is 0 into here, 0 take away 2 squared. What am I saying? Yeah, 0 take away 2 and then squared is 4. So see, suddenly at 0 it becomes 4. as in, let's see, it's whatever this value here, this value, -2 connected with that, but when you suddenly take away 2 from here, you've got to do catch up. So suddenly 0 connects up with there. So beforehand we needed -2 to connect up with that little point here. And then suddenly, if you take away 2 from that point, then suddenly 0 connects up with that point. It is a hard one to see.
I get it.
I just didn't understand that. You want to try it again, Miss?
I'm just gonna go into it.
You have to memorize that.
Maybe try some positives. So something like 4 would connect up with 16 on here, because x squared, 4 would connect up with 16. But here's 4 minus 2 is 2, and 2 squared, so now 4 is going to connect up with a smaller number. 4 is going to connect up with 4 minus 2, 4 is going to connect up with 4. So it's kind of like saying that this point, if you subtracted 2, where would it go connect up with? It's a hard one to see.
If it was what?
If it connected up, it is a hard one to explain. The best thing to do would be like doing this x squared one with a big set of, a table, like x is 1, 2, -10, manually working them out, and then manually working that one out, and you'll see all the values have just shifted 2 units. The heights have kind of shifted 2 units down, which kind of, I don't know, it's a hard one to explain actually. But yeah, vertical transformations follow the sign, horizontals go in the opposite. At some point when we do quadratics or something, and when we do transformations, we can do one to prove it.
What would it look like if it had both?
Oh, if it had both?
Yeah.
So if it had something like x minus 2 squared plus 1.
So that would move up 1 and right 2.
Yeah, every single point's moved up 1 and right 2.
Absolutely.
Yeah. So when we do transformations, I'll sort of do one from scratch with you, where we do a table of values and we plot the points for the horizontal one, so you see how it does mathematically kind of change it and make it move in the opposite direction. Okay, so back here. So how if we restrict the domain to being x is greater than 2, we put a 2, it's suddenly 1 to 1 and the inverse function does exist. So you're asked to draw in the line of reflection, which was y equals x here, and use it to sketch the inverse of the function below. So see, it's a quadratic, but they've restricted the domain. Domain is restricted, so the inverse function does exist, which allows us to draw it then. Function does exist. That's what that was for. So we can plot the line y equals x first. So like, it's got to go from 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and so on. Let's draw it. I like to label it to y equals x, so people don't get confused and think it's part of a function. And now let's do the inverse. So it's x-intercept, the original one, the x-intercept was 2, so what will the y-intercept be? So yeah, you see they kind of swap over a bit. Another thing you can think of is where they connect, where it crosses the line y equals x, they'll both connect there. And then, as I said, mine's stretched out. So that's kind of, and then this one is kind of like 1 2/3 unit this way, so this one should be 1 2/3 unit this way. Yeah, I'm drawing the right spot.
Where'd you get that 2/3 thing?
Yeah,
So 1 and 2/3.
Yeah, 1 and sort of roughly 2/3. 1 and roughly 2/3. It's hard for me to see this because it's so stretched vertically on the projector. This one maybe. So see, you've gone this way, you can connect here, you'll have another point here. That helps. What? I should just do it on the computer. Oh, no, it's time. Okay. Yeah, we can finish up there. So remember, you can be doing some of your topic assignment, doing some of the textbook is also a good thing. And then we'll finish this one up next lesson. So let's go to recess now.